Okay, so in this final discussion of rates and how to affect the rate of reaction, we're going to look at something called the activation energy. Now, this is a piece of information in addition to collision theory. So this assumes that a collision is occurring between two particles, again, particles A and particle B. And what it now requires, though, is not only must particle A hit a particle B, as we've looked at a number of times now. So particle B must hit particle A, as we keep saying. But what we're now also saying is, because what we've also been saying along the way is it increases the probability of a reaction occurring, because this suggests that not all reactions are successful. Not all collisions result in a successful reaction. That's because this collision must have a certain force. The collision must occur with a certain amount of energy, with a certain amount of vigor in order for the reaction to proceed. And this is something called the activation energy. And it's represented on an energy profile diagram like this. And what we have is particles A and particle B here. They have a certain energy of the system. And particles A and particle B will be constantly colliding. And this suggests now that in order for particle A and particle B to react and to produce particle C and, say, particle D down here, that they must change in energy. However, in order to do that, they have to go over this reaction profile here. They have to collide with a certain amount of, so say, excess energy than what they would ordinarily have if they were just by themselves. And they have to have this minimum amount of energy. And this minimum amount of energy is something called the activation energy. And as we say, it is the minimum amount of energy required for a successful collision to occur. So lots of collisions have been occurring. We change concentration, we change pressures, we change surface area, etc., etc. We change the number of collisions. Not all of those collisions result in a successful reaction, because not a lot of them will have, or not all of them will have the required energy. Particles A and B might have this amount of energy, they collide, but then their energy allows them to fall back down the hill, essentially. Imagine this is just like a hill. Two other particles may have this amount of energy. They collide, however, their energy is not sufficient to push them over the top, therefore they drop back down to A and B as unreacted products. However, if they happen to have the minimum energy, they can have more, but if they have more energy than is required, or at least the minimum energy required, they can collide and be pushed over the hill and then essentially roll down the other side of the hill to produce C and D. This will give us an energy change, which we'll look at in later examples. This one, while we're here, is an exothermic reaction. Therefore, this will release energy, so it'll get hot, like combustion, something like that. But essentially, what we now have is the activation energy, giving us an additional piece of information that we need to satisfy in order for a reaction to occur. And it's a minimum energy. So just to recap, if A and B collide, they have to have sufficient energy to allow them to go over the hill to then proceed down the other side to produce C and D as products. If they don't have the sufficient energy, they collide, they drop back down. They collide, they drop back down. They just reproduce A and B or don't react in the first place. Only if they have the sufficient energy here, which, as I say, is governed by this arrow here from the reactance line to the peak of the curve, signified as activation energy, the minimum amount of energy required for a successful collision to occur. So they must have both the activation energy and also collide. If both of those situations are satisfied, a collision will be successful and a reaction will proceed.